Hello again, everyone, and welcome back to the Platypus Hall at PyCon Online 2021. It is 2021. Next up, we have Mars Butterfield Addison with Python versus Space Junk. Mars is a PhD candidate in computer engineering at the University of Tasmania and CSIRO, and she's got a really cool talk lined up for us, so it's all yours.
Thank you. Hi, everyone. I'm Mars, and I just thought that I would like to say hello at the start because I won't have time at the end. My talk goes right up until the very end of this time slot, but I will be sitting in chat so I can take any of your text questions or via email or Twitter or anything you like. And I really, really hope you enjoy the talk. Thank you very much.
Hello and welcome to Python versus Space Junk. I'm Mars, and you might know me as the Martian Life on Twitter. I'm a PhD candidate at the University of Tasmania and CSIRO, and I do a bunch of other things, but my talk today is related to my PhD research, so let's stick to that. The focus of my research is how sensors not made for space tracking, such as sensors made for astronomy or this big radio interferometer, can be harnessed for space tracking without impact to its regular operation. This means that we'll improve the overall precision and reliability of location and collision predictions. So today I'm going to tell you a story about space junk. I'm going to talk about where it comes from, what we plan to do about it, and what we do about it right now. And there's going to be a little bit of Python at the end that you can play along on your own time if you want to have an idea of how we do these things. So let's start with the what is space junk and where does it come from? If you ask any person on the street, most people are familiar with about the first 1 to 5 satellites. So your Sputnik and your Explorer from the USSR and the US respectively, and Vanguard 1, maybe, known as the Grapefruit, which is the oldest remaining object still in space. And they might know a handful of newer, more significant objects, such as space stations, the ISS, or some of NASA's great observatories, such as the Hubble Space Telescope, or any of the hot topic telecommunications mega constellations such as Starlink. And Australians of a certain age will remember when Skylab came down, so on average I'm pretty sure that we as a nation are a little bit more aware of space stuff than other nations that don't have a space program. But those few things don't add up to this. So let's talk about what this is made of and how it got there. One big factor is that we have launched more things over time. There are more space-capable countries, there are more private launch providers if you don't want a country's space agency to have to do it for you. We have cheaper launch materials, we've brought down the price per weight of getting something to orbit, and that means that more people have wanted a piece of the pie. Down this end, in the last few years, we're now launching about 1,400 objects per year, and about 55 to 60% of those are just Starlink satellites, and that's not including anything that's launched to get them up there. It's not just more often, but on average we're also launching larger and longer lasting objects, which means that they have bigger and longer lasting impacts on the orbital environment over time. But space debris doesn't include satellites, so let's put our beef with mega constellations to the side for a moment and assume that everything that we take to orbit has a good reason for being there. Let's just talk debris. How does debris get to space? Well, we have satellites that have broken or run out of power, we have launch experiments, we have launch waste, and we have astronaut error. An example of satellites breaking or running out of power, such as Landsat. There are many satellites that have run out of power and become inactive, mostly after living a full happy life and fulfilling their purpose for maybe hundreds of orbits. They eventually run out of fuel or batteries. Some of them fail on launch. They've never properly detached from their launch vehicle, or their battery didn't connect properly, or something else went wrong, and they've broken as soon as they've left the bay. And that means they might never have fulfilled their experiments or their purpose. And now they're debris. We also have mass simulators, or otherwise called boilerplate spacecraft. And the most famous example of this is the Tesla Roadster, even though that doesn't actually contribute to space debris. Right now it's going around the sun. It might end up back in Earth orbit once it's gone around and come back. But a mass simulator is when you need to test your rocket, you need to know before you put some people in some spacecraft and launch them into space that your rocket can handle the right kind of weight at the right shape and the right weight distribution. So you build a fake spacecraft that's like one solid plate and has mass equal to about the astronauts so you're going to send and their equipment, etc., in one solid piece of metal, and you launch that, and they have to be deployed so we know that they're going to detach properly. Usually they come straight back down, but that's something else that we put in space that's there for a little while. We also have multi-stage rockets, such as this Saturn V, Saturn V, third stage. This one's really funny to me because a few years ago, there were all of these headlines about how we found this new object. We can see it. We can't see it very well, but there's something that the Earth has caught. We think it's going to be a comet or an asteroid that's been caught in Earth orbit because it's not associated with any launch, and now there's a new thing that we're detecting on the sensors. It must be a new tiny captive moon. Oh my goodness, Earth has got a tiny moon. That's so exciting. But it turns out when they actually pointed a high-powered optical telescope at it, it's actually a rocket. And they're like, well, none of our rockets from any of our recent launches are missing. How the heck did that happen? And it turns out, actually, if we propagate it backwards, this is the third stage from the Apollo 12 launch that has been all the way out around the sun and back, like the Roadster's going to do, and been caught on the return flight. Hilarious. Of course, most astronomers were like, oh, it would be very unusual for it to be a comet or an asteroid. It's probably not that. But it was still funny to find out that it was actually this thing that had been this long space journey. And also, there is the $100 million tool bag. Didn't really cost $100 million, but it was about $100 million worth of loss and cost of recovery and placement, where a shuttle pilot was coming to do some repairs on the outside of the ISS, and they had these special spaceworthy sealed tool bags, and they accidentally let it go and it drifted off into space and then came down and burned up in the atmosphere. So that was an expensive mistake. But also the ISS semi-frequently creates debris of its own, because if you have a module that you have to replace on the space station and it's not feasible to bring the old one back down, they just have to chuck it off into space. It's unfortunate, but it's true. So stuff we know where it came from gets registered in a persistent record called the Satellite Catalog, or SATCAT, with details of when it was launched and some of its physical characteristics, and then we know that it's up there to keep track of. But what now exceeds the number of things launched into orbit are the number of debris objects that are formed in orbit. So this means we've got the same amount of initial mass, but now broken up into more fragments. And this is dangerous because at orbital speeds, which is thousands to tens of thousands of kilometers an hour, depending on the altitude, a breakup will on average yield more than 10 objects that are capable of the original force destruction. That means if something this big, it's something this big, it's going to create at least 10 pieces that are at least as big that can smash into and destroy at least 10 more things that are this big. Which means we get this flow-on effect, but it's also a growing flow-on effect. Almost exponential. In some cases, it is exponential. There we go. It's exactly exponential on average. So in some ways, breaking into more and smaller objects is better, but they have to be microscopically small before they stop being an issue on their own. So we've got rocket body explosions, which are our main debris-forming events. We had some laws that were passed in different decades in different countries that mean that if you're going to launch something into orbit and it's going to have flammable material still on board when it finishes its mission, you need to either vent it out into space or drive it until it runs out of fuel, because we can't keep having these things blowing up and taking out things near them and creating enormous clouds of debris. It didn't really stop these explosions happening. They still happen semi-regularly. We've just started calling them energetic fragmentation events. These are some examples of satellites of rocket bodies that have blown up semi-recently since those laws have been passed. And actually, this BRIS-M, or BRIS-M in Russian, is a really good example, because actually 4 of these have exploded since 2007. The other ones are Chinese and French, respectively. Satellites sometimes just get old and break apart because radiation and heat for decades on end will do that to you. Quite often a certain design will be especially prone to breakup, which means that if you've launched a fleet of them, they'll all break up at about the same age. One example of these transit sats, they were a precursor to GPS, so they were a sat-nav constellation, where about half a dozen of them have broken up in the same way into pieces. Or the NOAA surface and weather radar sats, where I think there were 15 of them. Most of them are pretty recent. They haven't been up there for very long, and yet 3 of them have broken up into pieces. So basically, big solar panels and lots of appendages means that if you're at low altitude, you're going to be constantly dragging on the atmosphere until you just fall apart. Something can't take it. So now we're up to anti-satellite weapons, or ASATs. Here, red are the countries that have shot down satellites in the past, and orange are countries who have anti-missile capabilities, which means you have a missile that can shoot down other missiles, which we theorize would be capable of taking down a satellite in orbit if that ever took their fancy. Starting with the USA, in 2008, the US shot down a satellite with a ship-based surface-to-air missile. The target was a satellite of their own that had malfunctioned shortly after launch. And at the time, their explanation was that the orbit was decaying, and the fact that it still had hydrazine and beryllium fuel on board meant that it was an explosion risk if it managed to hit the ground. However, that seemed pretty strange at the time. We just went, oh, okay, even though you were one of the main countries that made this illegal a few decades ago, you go ahead and break your own rules. And it came out later that it was actually a highly classified synthetic aperture radar surface surveillance spy satellite that was the size of a basketball court. So nice cover, USA. Long before then, the US had already been the first to score a direct hit on a target in orbit in 1985, when an F-15 in a steep upwards climb at nearly Mach 1 fired a missile from 38,000 feet and hit a to-be-commissioned satellite nearly 550 kilometers above it. There's nothing dangerous about that satellite. It was just to prove they could, I guess. Before this, early US ASAT tests from the 1960s and the 1970s used thermonuclear warheads that were fired from the ground in missiles that were actually just full-on rockets. And that same Thor missile form factor was later used to launch satellites into orbit themselves. But anyway, back then they were far less precise at hitting something in orbit, but it didn't matter because a detonation in the upper atmosphere would release a huge EM pulse that would destroy anything within like 8 kilometers of it in the sky. And this was just because they wanted to make sure that if the Soviets ever launched a spy satellite, they wanted to be able to kill it before it ever made it to orbit, even if it took out their own sats in the process. Over in China in 2007, they shot a truck-mounted kinetic kill missile at one of their own Fengyun 1C satellites as a test. This event produced the most space debris out of any single fragmentation event in history. They made 3,500 plus fragments from one satellite that was like 1.5 meters cubed, thereabouts. I'm estimating from photos I've seen of them standing beside it. And India joined the ASAT club when they shot down their own Microsat R in 2019, which again was about a meter cubed. It just fragmented less. And then there's the classic two things hit each other in space. The most famous of these is definitely the Iridium V Cosmos showdown in 2009, where both of them lost and produced about 2,000 fragments of 2 tons of debris. And half of those rocket explosions that I talked about before have already caused flow-on collisions with other objects. These happen pretty regularly. One of them took out another rocket body, and the French rocket managed to take out a tiny French microsatellite, so they were extra sad about it. And the Breeze M is just a matter of time. They've made so much debris. But there are also a bunch of near misses, or collisions with smaller objects where the damage doesn't entirely break apart a larger object. And we only know about these if one of the involved satellites is large and new and active enough that it has cameras on the outside to look at its own body. Or months later, when we figure out that actually its orbit must have changed at a certain point and we manage to extrapolate backwards and think, it must have been hit by something with about this amount of force at this time. So this is a Sentinel-1A, and one day they were checking its outside cameras and they're like, wow, that's a big dent in our solar panel. When did that happen? And they had to look at how its orbit had changed over time. Even the ISS gets hit, which is pretty scary for the astronauts that are in there at the time. The ISS had to dodge space debris 3 times in 2020, and still, when they were performing routine inspection of the outer hull, they found something had punched straight through the Canadarm, which is responsible for grabbing and docking incoming spacecraft. They didn't even know they'd been hit, and thank goodness the arm is still working, because if it wasn't, that's an impossible thing to replace in any timely manner. So here we have considered the growth in the number of objects in orbit from the disintegration of single objects. Note the years here are skewed because objects are indexed by the year that the original object was launched, not the year they broke up. So that big spike in 1999, that was the 2007 Chinese ASAT test. Those 3,500 fragments from that one thing. So what should we be doing about this problem? And what is stopping us from attaining those ultimate results? Well, the ultimate goal here is a combination of awareness, legislation and treaties for prevention, and then ultimately active debris removal, which means to bring down things that are already up there, usually by sending something up to get it. There are lots of ideas bouncing around for ADR, some ideas such as attaching sails or targeting with laser brooms, mostly aimed to slow down an object until its orbit will naturally decay. It will fall down on its own. But there have also been some more ambitious grabber-type plans, such as this one from the ESA, where it looks like something out of an arcade machine that's going to go up and nom all the satellites and then drag them down. Or bring them back to a spacecraft. There have been ideas for those, but none of those prototypes have been tested, where they get something and then bring it back to the mothership. But ADR is like the holy grail of space debris research, but no option is really proven generalized or scalable or reliable enough to be deployed at scale and to make a dent in the orbital population. And so a continued significant failure rate will also contribute to the problem if we keep sending these prototypes up and they're not doing a good enough job. And there's no foreseeable future where we manage to scoop up everything in orbit and this ceases to be a problem entirely, because we will always need some things in orbit despite the constant risk. So we do need a stopgap. So what do we do about it today? In short, we keep track of where everything is, and we use that to predict where everything will be, and then we maneuver things out of the way if they go and hit each other. This is very much like air traffic control, but for space. We call this space traffic management, or STM. But the air traffic control comparison is kind of false, because STM is so much harder in so many ways. You don't have a transponder on every satellite that tells you what it is and where it is, and you can't use GPS or sat-nav constellations to triangulate where they are. They don't have reliable tracking of where they were in the past, and even if we knew where they were, that doesn't mean that we can necessarily point them on the path that we want to. Most of them can't be maneuvered. It also means that over time, we can't just use a linear path to predict where they are, even if we could tell them to follow a specific path, which we can't, because they have complex movement as they drag on the atmosphere. You could point them in a straight line, that doesn't mean they're going to stick on it. And then they're also impacted heavily by random events such as solar flares that change the pressure around the Earth. So we put stations all over the globe to monitor the skies, such as this one from Hawaii that I think looks like a sci-fi landscape. That's why I picked this photo. And this figure shows a field of view for all the ground-based sensors in the US-operated Space Surveillance Network, or SSN. It's the largest network of sensors worldwide and even incorporates data from 3 satellite-based sensors. Other networks operated by space agencies or research institutes tend to be only one or a handful of sensors. And there are a few commercial companies which also track sats, but then they sell the data back to satellite operators for a small fortune. They're all pretty similar in that they tend to concentrate in the northern hemisphere. So Australia is super in demand for space traffic management because we can simply see parts of the sky that they can't. Here in Australia, we actually just turned on our first AU-based sensor for the Space Surveillance Network in WA, an optical telescope that they shipped over from New Mexico just for us. And they also operate a C-band radar from the same site, also for space tracking purposes. An Australian company, Silentium Defence, has just started building a dedicated radar array in remote southern Australia, and a few Australian observatories such as the Murchison Whitefield Array in WA have had some success in their experiments to locate space junk. Here you're probably thinking, but we have so many telescopes here, so many observatories in Australia, why aren't they all tracking space junk? We actually have a notable amount of observatories in our country. But there are 2 simple answers to that question. 1, those systems are needed for astronomers to do their work. And 2, they're not the same as what we need to track space junk. These both amount to, why would we waste time that we could be using to do astronomy well, just to do space traffic management poorly? And of course, some people are working on it. Myself and the engineers at ATCA and CSIRO Space Science are doing experimentation and adaptation for the CSIRO observatories. And there's a fellow at my university who's working with the professors from physics to do the same for UTES sites. And I know people at various universities around Australia are doing the same. But it's a super amount of work, and there are some key limitations. One is that the design constraints and priorities of a telescope designed to look at deep space are just different at a software and a hardware level. Deep space telescopes commonly point at one thing for days or longer to build up an image that may be only a few pixels wide. The most important thing is that the telescope can stay as stable as possible while tracking the Earth's rotation, and then that it can reacquire the object on consecutive days, so they can get as much information as possible out of those few pixels. Space traffic management, on the other hand, just wants as timely as information as possible. So if you observe this triangle as a representation of the competing constraints of an imaging system, we can picture this as the amount of pixels, the amount of colors, and the amount of frames in a video. If you want more pixels, you get less frames and colors. If you want more frames, you get less pixels and colors. And if you want more colors, you get less pixels and frames. So while astronomy is solidly in the as many pixels and as many colors as possible, please, space traffic management is solidly in the give me a snapshot as often as possible at almost any cost to quality. Not just that, but the mounts can often prohibit continuous tracking across the sky, even if they could slew at that speed, which they probably can't. So if we picture my hand as a telescope, a space tracking telescope could ideally track something as it goes all the way across the sky. For example, the ATCA telescopes can't actually do that. They have to track up and then spin all the way around and go back down. This also means that they have a slight blind spot immediately above them. And that is nowhere near fast enough to track something going across the sky. You can see how that would make them lose it in the middle. But it turns out that even the normal tracking rate isn't fast enough to hit something in low Earth orbit. They're just going too fast overhead. And then, even if you manage to track something across there, you manage to catch the data that you're looking for, the radio receivers are focused specifically to eliminate transmissions in the near field, aka anything nearer to Earth than the great distances it was designed to look at. And it gets worse from there, because an optical telescope can't reliably observe a dark object at such great distances unless it's in darkness, but also being lit. This means it has to be nighttime, but near enough to dawn or dusk that the sun is just below the horizon and the satellite is near the horizon, it will be hit by a glint. And that way we can see it. It just means if we did like a ray trace from the satellite to the telescope to the sun, they can see each other, but the telescope and the sun can't see each other. And also, optical doesn't work if it's too bright or overcast. But then you get a radio telescope to look for a dark object. It needs the reflection of a transmission. Transmissions that may be perturbed by going each way through the ionosphere. And why would an astronomy telescope be built to transmit a signal? It wouldn't. Very few can. That is, unless it was built especially to speak to spacecraft. Here in Australia, we have the Canberra Deep Space Network in Tidbinbilla that is responsible for talking to spacecraft such as the Mars orbiters for NASA whenever the Spain or California stations are facing the wrong way off the Earth. So about 30% of the time, we're it. We're the answering machine for everything that's out in space in that direction. And most receiver-only observatories in Australia try to observe space junk using reflections from Tidbinbilla's transmissions. But they're so busy wrangling all the spacecraft that their time to do radar experiments is very limited. So we're back to thinking, okay, fine, we'll just build custom sensors for space traffic management then. But unfortunately, they cost millions, or more often billions of dollars each, and we need to cover the globe and then have even more to provide redundant information. And dedicated systems for space traffic management suffer the same problem, and they can't be effectively used for astronomy, or depending on the design, even any sort of near-Earth object imaging for things such as comets. So the value proposal is solely on the basis of doing that one task and being a good global citizen. So you can see how our country might not be the best at that. But how does it work? So there is a generalized process of 5 or 6 steps, but each of these is terribly understated to be described as a single step. But first, you have to identify an object that you want to look for or a region of space you want to look at to target a specific object or objects. Then you have to transmit a signal if you then want to observe a radar response. You have to collect data using some optical or radio sensor. Then you have to analyze that data to identify and locate objects, which is many steps of its own because there are lots of things you need to know about it. Then you need to predict the future trajectory of observed objects. So if it's here, where will it be? And then you need to adjust the trajectory of objects when necessary. So from step 1, you figure out, already based on some previous locations of objects and predictions of where they will be, what part of the sky you need to look at. Before you even start step 1, there is some error. It cascades. Then, targeting requires conversion between geocentric versus topocentric coordinate systems, which means if you have, brought a planet here for this, if you have the center of the Earth acting as the coordinate system's origin, and then you have X, Y, and Z outwards like you would have in a 3D engine, versus if a random point on the surface of the Earth, such as here, is the origin, and then you have coordinates to rotate north, rotate east, or go up altitude. So you can see that they don't go one-to-one, even if the Earth was a sphere. But it's not, it's slightly flat. And then also, the surface of the Earth isn't completely regular. So already that introduces slightly more error. If you transmit some noise, that means finding a band on the spectrum that you're allowed to transmit noise on, and also getting individual permission from various space agencies for each transmission that you do to check that this won't interfere with their spacecraft. And if Big Daddy NASA says yes, then you collect the signal in your big expensive telescope or telescopes or radar receiver or some other sensor. And the signal has now traveled a huge distance through the ionosphere out, back through the ionosphere, potentially introducing error. And the hardware itself is prone to error from everything from temperature to nearby mobile phones to wind speeds, everything. And then digitizing and discretizing a continuous analog signal then means losing more information. You then have to use things like Doppler to figure out where the thing is, how fast it's going, and in which direction. You have to get all those relative to Earth, not relative to the telescope, which means doing that translation you just did backwards, but also the telescope is on a rotating Earth, so it's moving as it's tracking. So you have to do that translation backwards for every frame, every integration window. Then you have to figure out from context and what limited information you have, what object it is you're pointing at, so you can associate it with previous records of where it's been. You have to classify how it's moving right now, because if it's tumbling or it's being maneuvered under power, that's going to impact its trajectory into the future. And these are all super hard to do. Source locations are often imprecise, but the rest can be outright wrong. Then you have the prediction of where a satellite will go in the future, which is maybe the hardest part of the whole process. Even if something is in a stable orbit, the models used to trace a path into the future are complex. They're called propagation models, and they have to take into consideration everything from solar pressure to atmospheric drag to Earth's magnetic fields, all interacting with each other. So let's keep that in mind. It's called propagation models. Being such a complex physical simulation, we don't typically have the resources to fully compute it to any great level of granularity. Instead, most use a heuristic model called SGP4. It introduces an average of 1 to 3 kilometers of error per day, which means we need to see every object at least once per day to even be able to reacquire it later, for it to be easy to find again. And if we want actually useful predictions, we want to catch it even more often than that. Every single one of those thousands of objects. But say we do all that for every object in space, every day, and we now have a good idea of where everything is and will be. Now we just move things, right? Well, no. Even that's hard. First, you don't get a reliable pinpoint location of where each object is. You get a little bit of error along each of the 3 coordinate system axes, so a long track and cross track and radial, which kind of makes this long spheroid of satellite could be anywhere in here. And the thing it could hit, it could be in its own spheroid, and you have to check whether these 2 things intersect, which isn't a yes-no, it's more like a weighted probability. If they do intersect, you have to check if either one of them or both of them actually have the ability to move, which doesn't just mean it was designed with maneuverable jets, but it also means does it have enough power or fuel to do so right now? If yes, compute a new trajectory for the movable object, and then for each potential trajectory, you have to check, is that going to still hit the original thing or anything else down the line that's worse? If yes, go back, do it again. And if no, you have to calculate what instructions you have to send the spacecraft so that it will get onto the new orbit that you are aiming for. And then once you've sent those instructions, you have to try and figure out as best you can whether it actually moved into the orbit that you wanted to or it needs further adjustment. And if we do all of these things well, then we can prevent some types of collisions between objects where at least one of them can move some of the time. All that work, and that's the best we can do to keep things safe in orbit. So where does Python come into this? So if we look at this very generally, there are usually 3 systems involved in that pipeline. There's the thing that controls the telescope itself, which may be a single computer. There's the thing that does the majority of hard number crunching and the initial signal processing. This may be a supercomputer. And then there's the thing that gets the STM-specific information on the end, which, again, might be just like the scientist's computer or the researcher's computer. And the early steps are pretty low level and they need to be super fast, so they tend to be C-like. And the middle step really depends on the other systems of that specific observatory. But the last is done by individuals or they're application specific. So they're often things like MATLAB or Systems Toolkit or custom Python. And this is relatively recent. It's happened as new players have come onto the scene. So basically since like the 70s or 80s, when before then the only people doing this stuff was NORAD. So more physicists and engineers were starting to have to write code, or you had devs who had to collaborate with the scientists and physicists. So we ended up getting more Python over time. A bunch of squirrely scientist libraries that were from C or Java or even obscure languages started getting Python wrappers. We got more dedicated Python libraries, and also old tools that people had made just for themselves started getting appropriate open source licenses. Here are the 2 that are maybe the most popular nowadays. You may notice that one of these is written by a space organization and the other one basically just by one person. So where commercial companies and military space tracking organizations were once super opaque and still are, tools such as these have become so widely used and tested that people are starting to switch. So it's very much like that XKCD comic, except that the infrastructure here is responsible for all of space safety and that one random person is from Ohio or somewhere in France. But the problem is far from solved, because the limitations of the models used for these tasks are known, and still new tracking operators pop up and decide to roll their own and keep it proprietary. They don't realize that all of the models suffer from similar limitations because that's just physics. They go, I can roll my own, it's going to be better, it'll be great, And we're going to sell the fact that we have our own proprietary models. We're going to tell everyone it's better than everyone else's. So while we're getting better at data sharing between space tracking providers, and we're now using all the same underlying astrodynamics libraries for things like orbit determination or propagation, the whole domain still suffers from a severe lack of standards, and nobody contributes back to core. So even if they're sharing data, they're not sharing implementations, because STM data is still worth too much to help other people make it free. Or so they would have you believe. So if you own an observatory that can do space traffic management tests, or you personally can force a commercial space tracking provider to contribute back to source, do that. But if you can't do that, and you know Python, here are some things you can do. You can develop faster or more accurate propagation heuristics, and you can benchmark existing propagation models and anything new you make against each other, which means that you can see that for different types of objects of different orbits, they introduce different types of errors or 10 different ways over time. You can develop special case models for hard to track behaviors, such as objects that are like small or too far away or really fast moving or tumbling or have really irregular orbits. Or you could implement easier multi-threading or GPU support for models, because as different observatories slowly switch from having like FPGAs or like sun systems, they're all going to GPUs and cloud. That's going to make it much easier for the scientists who don't know this stuff if you're a Python dev. Lots of these places need Python devs. And the work to get started with a minimal example is to go to a website that has every detection of every satellite since the dawn of the internet, in your preferred format of CSV or JSON or multiple others. And then you install a library where these steps are already inbuilt, and then you can just play around replacing different parts of the pipeline and see what happens. You can take a detection from yesterday and predict where it will be today with your model, and then you can compare where it was actually seen today, and there you go, space tracking. So if you need a hand getting started, you can go here. I've got some code for you, and let me know how you do. Thank you for listening. Probably don't have time for questions because I had so much to cover, but if you like, you can tweet at me at The Martian Life, or you can email me at hello@themartianlife.com. Thanks for having me.
Thank you so much for your talk, Maz. That was really informative. Maz has been working really hard on answering a bunch of questions in text chat as well. We're going into a 45-minute break until the next talk. So get up, stretch your legs, walk around. I highly recommend people check out pycon.org.au/social to see the social events planned for tonight and for tomorrow. There is a dinner video meeting tonight, which should be really good, and also some RPG sessions that are still open for applications for tomorrow, as well as some other cool stuff such as Mario Kart. Lightning Talk submissions have closed. They closed at 1 PM, so they'll be on at 11 AM tomorrow if you want to watch. But check them out. I'll see you all another time.